Hi everyone, this is another version of a Dalton's law of partial pressure style problem. Here we go. If 5.00 grams of hydrogen and 14.0 grams of nitrogen gas are placed in a 12.0 liter container at 25 degrees Celsius, what is the total pressure? Also, what is the partial pressure of the hydrogen? It's two questions in one. I forgot the question mark. It's two questions in one. Let's see what we have. 5.00 grams of hydrogen. 5.00 grams, that's a mass. And hydrogen is H2. And we have 14.0 grams, that's a mass, of nitrogen. That's N2. Are placed in a 12.0 liter container, there's V, at 25.0 degrees Celsius, T. What is the total pressure? P total. Also, what is the partial pressure of the hydrogen? I'm going to write it like this. I'm going to put P H2, the pressure of just the hydrogen, question mark. It's two questions in one. Let's focus on the first part initially. What's the total pressure? P total is N total RT over V. But we need the total moles, but what we have are two masses. It's going to turn out to be like this. The first mass over the first molar mass, and then the second one. RT over V. So it's going to be pretty loaded up with numbers, and it's a real challenge with our calculator. However, still okay. So we have mass over molar mass twice. One time for the hydrogen, one time for the nitrogen, and we're going to add them together in those brackets. Turns out to be, let's see, the first mass is 5 grams, 5 grams. Hydrogen is H2, so the molar mass is its atomic mass twice, 1.01 plus 1.01. That's 2.02 grams per mole. Now we're going to add the second mass over molar mass, which is the nitrogen. We have 14.0 grams over, the formula for nitrogen is N2. It's twice its atomic mass, 14.01 twice. It's 28.02 grams per mole. We're going to take that and multiply by R and then T. R, the ideal gas constant, 8.314 kilopascal liters per mole Kelvin. And the temperature converted into Kelvin is 25.0 degrees Celsius plus 273.15. This is all of it, pretty big, all divided by the volume, 12 liters. Lots of buttons to push for our calculation. We have 5 over 2.02 plus 14 over 28.02 times 8.314 times 25 plus 273.15 divided by 12. We get 614.51797776, which, when we think about the significant digits, all of these numbers in the question have 3 sig digs, so we want our answer to have 3 as well. 614.5 rounds up to 615. And this was the pressure kilopascals. That's the total pressure of this system. Because it was the total pressure, we use the total moles. The pressure of just the hydrogen is going to be the moles of just the hydrogen. So it's going to feel a little bit repetitive. However, if we made it through the first part, the second part, it's almost already there for us. Just the hydrogen's pressure, it's going to be just the moles of the hydrogen, which is represented right here. It's this 5 grams over 2.02 grams per mole. That's grams. Times 8.314, the ideal gas constant, times the temperature, over the volume. Before we work it out, just look at the difference between these two calculations. It's the same volume, the same temperature, the same ideal gas constant, where here it was the total moles to get the total pressure, where here it was just the hydrogen. Instead of the two different gases added together, we focused on just one. We focused on the hydrogen because that's what we were being asked to do. I'm going to do a calculation now. I have the expectation that my answer is going to be way less than 615. I'm typing it in. 5 divided by 2.02 times 8.314 times 298.15 divided by 12 equals 511.3075701. When we round that off to our three significant digits, we have 511 kilopascals. We need to take our time and we'll arrive at the answer using the ideal gas law in isolation. Instead of adding the total moles together, you can just focus on the moles for the chemical that the question is asking us about. And I hope that helps.